Hello everyone, this is part 2 of our diffusion homogeneous reaction problem. So we have a pore of length L and it has a radius RP. Inside this pore there is a homogeneously distributed catalyst. As the gas A is diffusing, it reacts, so that's why it's called a diffusion homogeneous reaction problem. From part A, so the previous video, we found that differential equation that describes the concentration as a function of Z is dAB, so the diffusivity, times the second derivative of the concentration with respect to Z squared. And this was equal to K, our reaction rate constant. So now in part B, we are asked to find the two boundary conditions which are necessary to solve this differential equation. And once we solve that, basically, we can find our concentration profile. It's a second order differential equation in Z. So that means that we'll need two boundary conditions. We look at this problem as a one-dimensional problem. And usually finding boundary conditions is pretty straightforward. You want to look at the two ends of your volume or where you're working. So here we know we're working in the Z direction from Z equals 0 until Z equals L. Okay, so we know that we're going to have a boundary condition here is equal 0 and a boundary condition Z equal L. So let's start with the easy one, which is a boundary condition at Z equals 0. So it's basically given by the problem. They tell us that the concentration at the mouth of the pore is Ca naught. So that concentration is specified. So our first boundary condition will be at Z equals 0, which is the mouth of the pore. The concentration of A will always be Ca naught. So this is a type of a prescribed concentration. Now, the second boundary condition is a little more tricky. We cannot have a crossing. So what that means for our second boundary condition, we see that no A can cross. If I look at the flux of A across the interface here at Z equals L, well, if no A can cross, then that means if we counted the number of A here that is crossing over time per unit area, then that would be 0. So we would have a flux NAZ at Z equals L is basically 0. So these are basically our second boundary condition is a prescribed flux. However, we cannot use it directly in this form. We need to have something that relates to concentration because our differential equation only has concentration terms. So the way to solve this issue is to use Fick's law. From Fick's law, we know that the flux in this direction is equal to minus the diffusivity times the first derivative of concentration with respect to Z. So basically the concentration gradient. So now if we say, oh, this is 0 because no A can cross, also this dAB times derivative of CAZ, and this is going to be evaluated as equal L, is going to be 0. So since dAB is a constant, we can simplify it. And basically our second boundary condition will tell us that dCA dZ is equal to 0 at Z equal L. So to summarize our part B, basically the boundary condition 1 is that at Z equals 0, the concentration of A is Ca naught, so prescribed concentration. And boundary condition 2 is that at Z equals L, the derivative of the concentration with respect to Z is equal to 0. This is a no flux condition, and this is a prescribed concentration condition. Then we move on to part C. We ask it to solve the differential equation. It's pretty straightforward, so let's start with our differential equation. So it's going to be dAB, second derivative of Ca with respect to Z is equal to a constant, okay? So first step is we want to rearrange this. So we're going to bring this downstairs here. So at the denominator, so we divide both sides by dAB, and this is going to be simplified to 1. And what we get is second derivative of Ca with respect to Z squared is equal to K divided by dAB. And we can see this is still a constant. So our starting point is second derivative of Ca with respect to Z squared is equal to K divided by dAB, okay? And then I can rewrite this as derivative with respect to Z of derivative with respect to z of CA equals k divided by dAB. Okay, now what I'm gonna do is I take this dz and I bring it here. Okay, and I'm gonna rewrite how that looks like, and we get dCA dz equals k divided by dAB dz. Okay, now next step is, so right now we're in a good point because we have a differential here d and a differential here in dz. Okay, and now we're going to integrate. Okay, so we integrate on the left hand side and on the right hand side. We can do this integral and it's going to look like this. Basically here we're doing the integral of just dz is equal to k divided by dAB times z plus a, where a is an integration constant. We can do our separation of variables again. So second separation of variable, and we get that dCA is equal to k divided by dAB z dz plus a dz. Okay, and then we're gonna carry out our second integration. Okay, so we have dCA equals k divided by dAB z dz plus a dz. Okay, so let's carry out these integrals here. This is just going to be CA is equal to k divided by dAB z squared half plus a z. And a little reminder, integral of x dx is x squared half plus a constant integration b. So this, and we're going to add another integration constant integration. Easy way to remember these integrals is you do, in general, x to the n integral is going to be x to the n plus 1 divided by n plus 1. Okay, so yeah, we basically found our general solution, just the integrated version for the differential equation. However, we still don't know what this a and b are, this integration constant, and this is basically where we need to use, so basically we use the boundary condition 1 and boundary condition 2 to find the integration constants a and b. Pretty straightforward. We can start from, let's start from boundary condition 2. Derivative of CA with respect to z at c equals L needs to be 0. So let's calculate the dCA dz. There's two ways to do it. We either take the derivative of this function up here that we just found, or we just look step back and we look at our, what we got after a first integration. And after first integration, we had basically k divided by dAB times z plus a needs to be equal to 0. Now, this needs to be evaluated at z equals L. So instead of having z here, I'm going to write L. We can rearrange this, and you can see this is a constant plus a. So a is going to be equal to minus KL divided by DAB. So great, we found our first integration constant. Now we apply our boundary condition 1. We know that at z equal 0, CA is equal to CA naught, so a constant concentration. So CA naught is going to be equal to K divided by basically 2 DAB times z equal to 0. So this is times 0. This is basically the z squared plus a, which we just found, but it's going to be multiplied by 0 again, and plus b. Okay, so we find this first term cancels and the second term cancels too, so we find that b is equal to CA naught. Okay, so we found a, we found b, now we just summarize everything. And we find that the concentration of a as a function of z is k divided by 2 DAB times z squared minus KL divided by DAB times z. So this was our a, plus CA naught, which is our b. Okay, so this is how our concentration profile looks like, and we can try to quickly sketch it. If I'm plotting CA as a function of z and this is z, so basically here we have L and this is 0, and this is CA naught, and this is concentration 0. So our boundary condition says that as z equals 0, the concentration will be CA naught. So this point needs to belong. And then we also know that at z equal L, the first derivative, so dCA dz as equal L is 0. Its slope is 0. So slope, this is going to look like a parabola, and it's going to drop like this, and then it's going to be basically 0 slope here. You can know that the concentration drops because A is reacting to B, but at the same time that it's reacting, it's also diffusing in the Z direction. Thank you for watching this, and please let me know in the comments what topics are difficult for you guys, and I can work on preparing new videos on those topics. Thank you.